Hello, good afternoon, everybody. I think we have started our broadcast. My name is Ben. I welcome you from wherever you're joining in the world. Some of you might be at Astro, some of you might be sitting at home, and some of you, probably the majority, will be watching this after it's recorded. But just know we are recording live, so if you are at this meeting, please feel free to type in as many questions into the question bar, and there will be plenty of time to get to those questions. You will be greatly relieved that I will not be inundating you with slides today. I'll basically show an outline slide and then get going into a demonstration. What we're here for today is really to talk about how physicists and clinicians can very, very easy and pretty much automatically start to navigate the new era where auto-segmentation will start to dominate the contouring, in particularly of organs at risk, I think. We're going to talk about a software product called StructSure from Standard Imaging. I helped develop it. I think we first came out with it over 10 years ago. I don't quite remember, with a patented method for scoring. The reason we came out with it initially was to help physicists commission autoseg. It just so turned out that auto-segmentation really wasn't quite ready to wear or pret-a-porter at the time. But with the new AI-based technology that's ubiquitous in our world, not just in medicine, it's coming fast and furious, and I have seen so many impressive models, and I'm not easy to impress. So that's really good news. Better late than never. There is rampant, I've done studies and studies, there is rampant variation in contouring, not only of targets amongst physicians, but also of organs, critical organs and volumes amongst physicians, dosimetrists, et cetera. And that remains to this day when humans are doing it. We're going to talk about how you can figure out how to buy the best autoseg services, how to validate and commission your systems for the first time, and then how to basically keep doing regression testing because they will be constantly being updated. So let's just talk a little bit. I just prepared this one slide and then I'll show you a demonstration. We know that automated contouring will be less variable than manual contouring, and that's a good thing. We have to drive out all manufacturing across all technology and markets. You want to drive out variation, but it must also be as accurate as or more accurate than your best human anatomist. So how do you prove the accuracy when you are converting to this new world of auto segmentation? It's going to be the siren song to get you to go to automation because it's going to save you hours and hours and hours per plan. It's going to save you a lot of time when you're doing online adaptive. And if it's accurate, it really is going to be something we've needed for a long time. But just automation in and of itself can cause more harm than good. You may be driving out systematic differences, but are you creating systematic errors? Or are you driving out systematic errors? That's what we want to get to. And we have a very simple technology and very inexpensive technology that Standard Imaging has that will help you. First, how do you choose which AI product or service is best for you? You have a lot of options now. I was just on the Astro show floor a couple days ago, the day before it opened, and there are a good number of very talented startup companies that are focusing only on AI and particularly on auto segmentation. I could name quite a number of them, but I wouldn't want to start naming them now because I might leave some out that I don't know. So in the sake of being fair, I won't mention any by name, but there were a good number of them that have booths. And then of course your major vendors, TPS vendors, LINAC vendors, they're going to have their own offerings as well. So you have a lot to choose from. One thing I'd like you to think about, because I do think this is the way it's going to go, I don't think that it would be good if you choose AutoSeg kind of like you choose a TPS vendor 10 years ago, which is, well, we've chosen this one, we're going to stick with it 3, 4, 5, 10 years. There's a lot of inertia in that. I don't think there's going to be a lot of inertia in AutoSeg because you're going to have a lot of options. I think auto segmentation will become a service. Probably most of the startup companies, if the really smart ones, will not try to say buy ours over everyone else. They're going to say, hey, subscribe to ours, and we're going to show you how good you are, how good ours is, and you pay for what you use. So it should be like a subscription service, maybe even a pay for use service. Well, that even doubles down on how do you verify that it's good enough to use? How do you verify it will pass the muster of your physicians? How do you document that you've tested it? How do you decide which modalities it works for, which body sites it works for, and for any given body site, which structures do you trust it for, and which are still a work in progress for you? These are all questions. They can create a big headache, in particular, probably in the United States, at least the physicist is going to be in charge of commissioning the treatment planning system. It's probably true internationally as well. So the physicist now has to make sure that a verification has gone on that proves that auto segmentation is accurate. So you don't want to spend a lot of time doing this, but you want it to be comprehensive and robust. So it needs to be validated for each structure, for each imaging modality. It will be pretty frequent because these models, especially in the early stages, they're going to constantly be turning out new models and updated models. So it's not like you're commissioning one for years. You're going to have to constantly recommission or at least run regression tests every time your vendors of choice update a model. So this is how you can do it with StructSure. That's the only slide I'm going to show. I'm going to go ahead and minimize. And I'll show you how easy this is. Now, I'm actually going to show a demonstration in 2 phases. The first will be, I want to show you the type of metrics that are generated so you can understand that. And I'm going to show you that in the terms of kind of a manually driven interactive comparison, which in and of itself will be very easy. But ultimately what you're going to be doing, and what I'll show you later, is running a batch analysis. So in theory, your only job is going to be, when you're deciding what to buy and proving what to use, your only job is to come up with your benchmarks, your standards. Generally, that's finding your best physician or physicians to come up with some standards, pull some patients you've done in the past, curate them to make sure you really like those, have some consensus from your expert or experts, and then you publish that internally as a library of standards. Now, anyone who says they have AutoSeg, you run them against your image, those image sets. They produce the structures that they produce, and you can then objectively and automatically compare it against the human drawn ones, where the human drawn ones are your standard at the time. So that's a process you're going to go through. You can have libraries that are many, many dozens, if not hundreds, of these standard sets. And the StructSure batch analysis feature is going to be really nice because you just basically click a button and then let the analyses happen, and it'll spit out this big spreadsheet of a comprehensive set of metrics. So before I show you what you can do automatically, I thought I'd show you what you can do manually, just so we can understand the types of metrics we're dealing with. So the first example I'm going to show is a very simple example. It's actually, it is of AutoSeg engine. Again, I won't mention any vendor names. I've worked with a lot of the vendors, and like I said, I'm really impressed with a lot of them. I'm really excited for the future of AutoSeg. But even within a particular model or body site, some things work really well, and some things, you know, you're going to have to be the judge of that. And you don't want to waste your time being qualitative. So let me first start with a head and neck example. What you're going to do in StructSure is first you're going to load data. Well, I want to load some images. Everything's DICOM, works with all the systems. You DICOM images, be it CT or MR, and then of course DICOM structure set. So let me find a patient I have here. Let's start with a head and neck example. Now, the primary structure set I'm going to load is going to be my human-driven. And it's not any human. It's really, like I said, it's the standard that your clinic has chosen. And then you get to select your AutoSeg is going to be your secondary. You can also compare one physician to another, one dosimetrist to another. Of course, you can do that because it's just structure sets. But here in the context of this presentation, we're talking about what the robots produced. One thing you'll notice immediately is when you load to structure set, it'll tell you everything that found a match. So those will be the things that are analyzed. And StructSure has some nice tools here where you can set what we call synonyms, ROI synonyms. So even if in the structure sets things have names that aren't exact, you can set up synonyms and it'll automatically know what to compare to what. So let's go ahead and load these data. Okay, the first thing you'll see is, and I won't show you all the tools, I just want to show you how simple it is. So here we can see the dashed lines are, in this case, the secondary case, or that's the AutoSeg, and the solid lines are what this particular, what this physician drew. So you can automatically see there are some differences. I mean, there's overlaps, but there's differences, and we need to understand how those differences manifest themselves. So we need to do some objective comparisons. In this particular case, we'll be able to look at the brainstem, mandible, cord, left-right, parotid, left-right submandibular gland. Over here, we have a navigation tool, so you can use this 3D view to kind of move it around. This just helps you find the slices you're looking for. You can turn structures on or off for calculation. You can turn them on and off for viewing. No problem. You can window level your images, all the tools you would expect to see. But let's jump into the analysis. So you can run analysis automatically where you load two structures and it'll automatically calculate the numbers. That's with settings. I've got it, so I have to hit the calculate button. So I'm gonna go ahead and hit calculate. Well, and that was pretty fast. So this is a fully volumetric comparison where each structure is going to be rendered into tiny little voxels, and these voxels can be smaller than, they can be about the same size as a CT or MR pixel, or they can be smaller or bigger, however you set it. That's another setting. I think currently I have this set to be 1 millimeter increments. So everything has a resolution of about 1 millimeter at this point. Let's examine just one structure at a time so I can explain the visualization. Let's just turn on the right parotid. Oops, I turned on the left parotid. Okay. So if I zoom up and I go through the axial slices, the green region represents what matched, the overlap. The red region is where the secondary data set, that is the AI, drew larger than the human. And the blue region is where the AI drew smaller than the human. So think of it hot and cold, where hot would be your secondary is bigger and cold would be where your secondary is smaller. It's that easy. And you can see there are regions, but really the errors aren't that huge. I mean, there's a few millimeters here. It may not be exactly what you want to see, but you do see it's in the ballpark. How do you start making conclusions then that aren't qualitative? Well, it's pretty easy. What you do with StructSure is you go to the analysis results tab here. And they're automatically sorted by the goodness of fit. So this is something called the StructSure score. We also will show you the volume of the primary and secondary. So you can see if overall it's larger or smaller. Of the two volumes, how much is common, or what's that green region of overlap? How much volume was missing, how much was extra? The dice coefficient, which is just the measure of overlap. Dice is a little bit imperfect though, because it doesn't really assume right versus wrong. So dice is pretty good if you just say, I have two things, I want to see how much they overlap. In this particular case though, you have a reference. Your primary you're using as your reference. So you don't want, a dice coefficient can doesn't really capture if one is you're trusting and one isn't. So we have the StructSure score, which actually in a three-dimensional sense, the bigger your error is, the more a penalty you can assign, and that's completely up to you. We're using a simple linear model where we have a 1 millimeter forgiveness region. So if you're off by a millimeter, big or small, you're not going to be penalized at all. And then the penalty will get larger and larger the bigger the difference is. So this starts to become a very sensitive metric. For example, look at the brainstem here, has a dice of 0.765. The StructSure score, which goes from 0 to 100, is only 44. That's because some of these errors you're going to see are larger. But let's go through one by one. First of all, the left submandibular gland is exceptionally close. If I just look down here, you can see all throughout the submandibular glands for this particular AI engine and this particular physician matched extremely well. And that's kind of, actually the right submandibular matched a little less well. And that's interesting. Why would there be a difference in the left and right? It's a great question that you can start to drill down on. But the mandible also scored very high, the left and right parotid. So overall, this wasn't a bad result, but you can go and let's look at the first one that say gets a score under 80. Here, one thing that's useful in StructSure, we'll show you the distance volume histogram. So these represent, of the voxels that did not match, how many were off by a certain distance. So this many on either side were off by 1 millimeter, 2 millimeter, 3, 4, 5. So you see most of the errors in this case are within 5 millimeters, a few here and there. So that's how you can start to look and see why this score starts to get low. And now let's look at the brainstem. This graph shows you something very useful. It says the AI model did miss a lot. It was a good bit smaller and up to 10 millimeters difference. So if we were to look at the brainstem going up here, we will see that overall the AI drew it smaller than this particular human did. Now, of course, you can ask the question: which one was better? But you are going to decide your own reference, and that's what the physician has to sign off on these. So you do want them to more or less match what the physician would have drawn if they were paying close attention. So here you see pretty much a systematic difference where the AI is just a little bit smaller, and that's manifest here by you seeing all this blue. Well, what other types of analytics do we give you? Well, first of all, the dice coefficient, the max difference. So in a three-dimensional sense, what's the most different point? What's the length of the vector of difference? The StructSure score, which is that weighted score where you start to be, it's very sensitive. If you start to get a lot of voxels that are more than, say, 4, 5, 6 millimeters difference, this score will drop quickly. It's very sensitive, but so is radiation therapy. You're painting gradients now that can change over 2 to 3 millimeters. And if you have an organ at risk, think of SRS, think of proton therapy. A few millimeters away can make all the difference in the world. So the StructSure score is really good and sensitive, whereas the dice coefficient might look high. If some of the differences are very large, StructSure score will become smaller fast. Total volume, common volume, and then this is nice too. The analysis of difference shows you the missing, the extra, but then how of everything that was different, what percentage was within 1 millimeter, what percentage was in 2 millimeter, within 4 or 5, et cetera. So in this particular case, let's look at the right parotid. You can see here that almost 99% of anything that was different was still less than 5 millimeters different. Whereas if we compare to the brainstem, that number goes down to 70%. So in other words, this algorithm is not predicting the human contour nearly as well for the brainstem as it is for the parotid. So you can really start on a per structure basis, start to analyze how you do this. And then we show you the distance volume histogram, raw data. And then if you want to actually see slice by slice analysis for each slice, each CT or MR slice, you'll see the max difference, the dice for that slice, so now it's two-dimensional, the StructSure score for that slice. This is helpful because now you can start to see, well, for many slices it's the same, but then as we get inferior or superior, for example, it starts to taper off. Now, a perfect example of that would be if we look at the cord. In this particular case, it's an interesting example where the AI for the cord actually wasn't bad, but what happened was it stopped at a different place than the human did. So in this particular case, you see a lot of differences being too big. Well, that's because the AI segmented the whole cord, whereas the human provided contours stopped here at this slice. So that would be a case where the AI isn't wrong, but you go back and you will actually segment more of the cord, because a good AI engine will find the whole cord on every slice. So here's an example of the type of results you can do if you're doing it case by case. Just to show you how quick it is, I'll do another manual one, and then I'll show you the batch. So let's clear everything and load up. I think I have another body site data set. I've got a lot of them, but I had to be careful. Most of them were labeled by vendor, so I just took a couple that I had anonymized. So this is a male pelvis. I believe it's still a CT. I have done MR analyses before. It works just as great. They just have to be on axial slices. So here's the AI. In this particular case, we're going to explore the left and right femur, left and right. Well, the matches we have are for the bladder, rectum, and left and right femur. So not a whole lot of matching organs. Run a quick analysis. The results are now done, and we can go to the analysis results. And here you see the bladder, as you would expect, was found very, very well. Left and right femur were close with some differences. We can kind of look and qualitatively, you can see some of these areas here, but otherwise not bad. The rectum showed a very low result, and what's interesting here, it's not because of what was wrong on any particular slice. This isn't a terrible result that we're seeing here for the rectum. Very good, in fact. What the difference is is the AI started to get bigger as you get superior. There started to be a systematic difference superiorly. And then the other big difference, I'm sorry, that was inferior. Superior, it simply stopped at a different place. So when you're here, you may want to truncate, or you need to realize, like, if the AI is going to produce something, if you have a question about where the contour should stop, inferior or superior or inferior, you need to make sure you're testing that. And this is a great way that StructSure it says it's got a low result, even though that where there are axial slices that are contoured, they match very well. It ends at a different place. And that's important, because if you just trust it and rubber stamp on an autoseg algorithm, but it didn't quite, if it was contoured larger than you would or smaller than you normally would, that's going to affect your DVHs just as if you had drawn them manually. So in this particular case, if I look at the rectum, what's interesting here is that if I go to the slice by slice data, if we look at the dice coefficients, they're really, really high here in the central part of the rectum. But then there are a lot of slices here where they were missing, and a lot of slices here where there was pretty good matching, but it was mainly up here at this edge. So that starts looking like a big difference. And even though the dice was 0.772, StructSure is sensitive enough to say, hey, you need to look at something. So here you might go back and again, decide, do you need a different gold standard, or you're now allowed to, now you have objective data to talk to the vendor and say, yours contours here, it stops at a different place. Can you train a new model? And if they can't, then you need to know you're either going to be adding on or truncating. So autoseg is not going to be a panacea until you really validate that it's matching what your best human would draw. So here's all the different types of analytics you can spit out if you do it manually. But ultimately, what you're going to be doing is you're going to be building a library of standards. You're going to be running autoseg, and you're going to want to do a batch analysis. So what we have there is we do have a batch analysis tool. You just click batch analysis. And what you'll load up is an actual spreadsheet. That spreadsheet simply contains structure set 1, structure set 2. So these can be from all different modalities, all different body sites. It can be a dozen tests to run. It can be 200 tests to run. This is now your automated validation. So let me go ahead and run it for you. In this particular case, it's 10 head neck comparisons, I believe. So you just load that up and the calculation has started. So depending on how many structures there are, this can take a little bit of time, but we're already 4 out of 15 done. And I know as a physicist myself, having automation is going to be key, because you're going to have to redo these over and over every time new models are released or models are updated. But you're also going to want objective output. You do not want these to be qualitative, and you also want them to be very sensitive output. If there's a difference, you want it to be easily detected, and then you can decide if that difference is clinically important or not. And that's going to be a structure by structure determination. But once you've set up your thresholds for passing, then every time you get a new model, you just run it and you get the results. So now what kind of results does the batch produce? Quite simple. It's exactly what you want. It produces a spreadsheet. And the spreadsheet in this particular case looks like this. So it will tell you what was my reference RT structure set, what was my comparison, and then each structure set can have any number of matched pairs. So it's gonna again then give you the ROI name. So I tell you what I'm gonna do. I'm actually gonna sort this by the ROI name. Because you might want to group those together. So here we have the glottic larynx, the left parotid, the right parotid. Now this would be a great case. You don't just validate autoseg for one patient data set. You need to decide how many are we going to produce results for that capture enough statistics that we can determine that this is going to be, it's going to cover our range of patients pretty well. So what is that number? That's a good question. Is it you want 10 representative data sets per body site per model? Do you want 20? Do you want more? Do you want less? What the good news is as long as you come up with them, your analysis is essentially going to be automated and for free. So I'll go back to the beginning. Your biggest challenge when you're introducing autoseg to your routine is going to be, say, to define what the answer key is. Say, we want it to be very close to this, and that will be very important. And then after that, the rest is easy. So every analyses here, let's just concentrate on a particular row. It gives you all those metrics that I showed you earlier. What's the volume of the reference? What's the volume of the secondary, or the in this case, the AI? What's common, missing, extra? What's the dice coefficient? What's the max difference in millimeters? What's the StructSure score out of 100? And then what's of the differences, what percent are within 1 millimeter, 2, 3, 4, all the way up to 10 millimeters? So this also gives you the ability to invent your own acceptance criteria. StructSure's not going to tell you what's good enough. StructSure's going to tell you just, here are the metrics. So you may say, we want the dice coefficient, and I'm just making this up. You want the dice coefficient to be 0.7 or higher, or 0.8 or higher. We want the StructSure score to be 70 or higher. We want the max difference to be within 10 millimeters, and we want of the different point, we want of everything that was different, we want 95% of them to be within 5 millimeters or something. So everything you would need to do that multi-criteria acceptance is right here on this spreadsheet. So then you produce these spreadsheets. You can have a logic built into the spreadsheet that automatically tells you what passes and fails, and your life should be pretty easy. So it's comprehensive, it's objective. If you need to do a drill down, so if you see any results, you're like, wow, that particular organ gave really bad results for this model, you just can load them up in StructSure. And that's where it's really useful to use this drill down analysis, so that you can visualize the differences. And you can say, oh, the rectum score was low, even though it matched on axial slices, it was low because the superior border was different on the AI engine versus Dr. Jones. So you can really start to make smart decisions and to make them quickly. I see that I'm getting up against my time here, so I'm going to go ahead and open up and see if there are any questions typed in. If you have any questions, definitely type them in, and I will see.
Please, after comparing the two sets of contours, do you draw the differences yourself, or the AI auto segmentation will do that?
After comparing okay, one of the inputs is going to be, this is basically a tool that's not used for every patient you do. This is used when you're commissioning and validating an engine before you start using it clinically. So one of the inputs is going to be your standard that you prescribe. The other input is going to be, what did the AI come up with? The differences are then going to be whatever they are. So the visualized differences, the blue region, the red region, you don't draw those. StructSure just comes up with them with you, or comes up with them for you, and then you can make conclusions off those. I think if I understood that question correctly. So you're not really drawing anything, but after the fact, you can go back and use these colored regions to determine what the differences were, and then use all the objective metrics to determine to what extent they occurred. While you're typing, or if you're typing, I'd say, if I had to estimate, let's see, as part of your AutoSeg, and I do think you're going to be over time working with more than one vendor. So your commissioning and your testing will be the same no matter what AutoSeg vendors you're working with. You may say, well, this vendor is really good for MR AutoSeg of certain body sites. This vendor's great for CT male pelvis. This vendor's this, and you'll probably use a lot of them. So your acceptance criteria and the technique you use, the technology you use to compute the differences will be the same. That would be StructSure. And then you make it automated. So if you had different vendors, you still can do that batch analyses, where some of the body sites your testing will be, they could have been from different softwares. So I would say, if you had, let's say you developed a regression test suite of 100 different data sets. Now that's a lot to curate 100 data sets for your validation. It's probably what you need to do across all body sites. But in the meantime, let's say you do 5 example patients per body site. So you're quickly going to have about a library of 50 standards. So I would guess, if you were going to do if you were going to commission 50 comparisons, you know, that's going to take you less than 5 minutes in StructSure to do all those calculations. So really, what we wanted StructSure to do here is to make your life easy, and make it so that your only challenge is answering that important question of, well, what is right? and you will have to tell the software what is right. And that then gives you something powerful to judge your autoseg based off of. Also, one thing I think is going to happen out there is some standards might start being exchanged. So if you start talking with your neighbors, your colleagues around the country and the world about, hey, do you have a good standard for head and neck or something? And if they decide to share the standard with you, then you can use that to validate as well. You would, of course, have to have your physicians approve what their contours are. And this is the thing that's not talked about a lot with AutoSeg is physicians disagree. And that's another reason AutoSeg won't save the day is because every AI-based AutoSeg engine has been taught. It's AI, it's deep learning, so it will be reproducing the whatever was fed to it by the vendor that trained it. So if it was trained by contours that your physicians don't agree with, by definition, that model is going to produce outputs you don't agree with. That's why it's imperative that you really take this validation seriously, because automated doesn't necessarily mean correct.
Looks like we had another question come through, Ben. Ultimately, we will need to decide whether we need to edit the AI contours or let them go. Any thoughts on automated ways to decide that? For example, if you had 5 radoncs contour the standard cases, you get a standard deviation across those, and if the AI is subsequently within those ranges, then it doesn't need to get edited?
Now that is a great question. So first of all, yeah, I bet all of your AutoSeg vendors, my guess is that when you buy the product, there's going to be some disclaimer that says, hey, we're not saying this is right. You can edit anything. You have to review it and you can edit it. And that may very well be true, that it's a great starting point, gets you 90% of the way there, and you want to go through and make some edits. That would be on a per patient basis, and there's no way to by definition, if the expert is editing a contour for any given patient, that's their way of approving it. But this was an excellent idea in this question. When you're validating, you're trying to determine, hey, is the autoseg within a normal, a difference that would be normally expected just off of multiple observer here at our clinic? And there you have to ask the question, are your different observers different by a lot than each other? If so, that's a problem in and of itself, because you don't want because the shapes of the contours for targets and organs at risk will determine the plan that's prescribed. So if your plan for Mrs. Jones is going to be vastly different because of the contouring by physician A or B, that's a problem we need to root out. So getting your physicians to agree and to come to some consensus is also kind of in parallel a goal you should have. So if your physicians or dosimetrists differ by a lot, it doesn't mean your autoseg, if it's within that difference, it should be accepted, because that difference might be unacceptable. But this is a wonderful idea that you're going to have some difference. There's always going to be a difference. So what difference do you accept? And here it's where that's all determining what is correct or not. I generally don't tend to like the idea, because I've done these before. I don't tend to like the idea of saying, here's 5 different observers, the autoseg kind of falls somewhere between all of them, so it's okay. That seems to make sense, but it all depends on whether that variation amongst the observers was acceptable or not. What I found to be actually better, but surprisingly easier, you get those same 5 physicians. Because remember, this is a validation process. You're building a library of standards that you're going to use. These are your tests. Think when you're commissioning a treatment planning system, you have an arsenal of tests. There's going to be water phantom tests, there's going to be standard tests, but then there's also going to be some patient simulations where you can do some measurements, et cetera. You're going to want to do the same thing for AutoSeg. So you're developing your library of standards here. Instead of using an ion chamber or a diode or et cetera, you're going to be using a structure set that's been well curated. So what I strongly suggest is you get your physicians in the room and keep kind of editing each other's structures until they all agree that, yes, we're happy with that. So you build a consensus. There are other ways to build a consensus if you have enough observers, where you can build a 3D grid and do ISO agreement lines. If you're interested in that, you can get a hold of me. I've got some technology that does that easy, and it pairs very well with StructSure. but you can't just do it with 2 or 3 physicians, because then it's not enough. That would be if you have more like probably 10 or more observers. But what your goal that I really think the goal should be, try to get all of your physicians to agree on what is right, and that's how you judge your AutoSeg engine. So that's why I said your biggest challenge here is to, first of all, be objective and unbiased when you're doing your validation, and validate against something that your clinic overall can say that's a very acceptable data set. And then you get those standards, and then you run your tests. One thing you might do is you could have each physician issue their own standard and put it in your library. And then when you run your AI AutoSeg, by definition, those comparison difference will be a little bit different based on the physician. So if you see any outliers, the AutoSeg really agreed with Dr. Jones, Dr. Smith, but Dr. White was totally different. That shows you that Dr. White is different than the other two. And that's a very useful thing to learn. And then you can kind of start driving towards that. You want to drive towards standardization of what you think a correct contour is. And you're going to have to do that as part of your AutoSeg implementation. And the industry as a whole should be doing it as well. And we're working on it. I was just part of a group that just started. We have over 700 radoncs internationally who are taking part in what we call C3RO, which is the Contouring Collaborative for Consensus in Radiation Oncology. And once a month, we do a contouring exercise where we don't say what right or wrong, but we just have all these radiation oncologists contour the same image set blindly. And then we look and see where was there a lot of variability and where was there not much variability. So we're starting down that very important pathway of determining, trying to understand the variation and drive it out. Because if determining really what is right is imperative before you implement auto segmentation. But my name's Ben. Feel free to contact me if you have any interest in like building consensus or being part of that big consensus. It's obviously it's free. It's kind of this philanthropy science project we're doing. But otherwise, if you have any more questions about how we do these computations, et cetera, certainly Standard Imaging can answer, or they can make a call to me and I can help out.